Okay, hi everyone. So this is our seventh video, and the goal is to calculate some Galois groups. So let me remind you of what we did last time. So this is from last time. We saw the following. We saw that if K is the splitting field of a polynomial f with coefficients in f, then the map from the Galois group of K over f to the symmetric group on the set of roots of f, the group of permutations of the roots of f, given by, well, let's just send sigma to, well, how sigma permutes the roots of f. I think we denoted this by sigma sub roots f. So again, nothing complicated is going on. It's just the same map sigma, but instead of considering on all of k, you're considering it just on the set of roots of f, and it's going to give you a permutation of the set of roots of f. We discussed why. So this map is an injective group homomorphism. Okay, now what you do is that, okay, so because this is an injective group homomorphism, this guy here, this Galois group, we can think of it via this homomorphism as a subgroup of this symmetric group. So let me give him, let's call this maybe 1. So via 1, we think of, or we can think of the Galois group of K over F as a subgroup of a symmetric group on the set of roots of F. So in other words, as a group of permutations of the roots of F. So now what we're going to do is that we're going to start calculating Galois groups, some Galois groups, and some Galois groups of splitting fields of some polynomials. And then because of this result, well, we're gonna try to describe the Galois group as a group of permutations of the roots of the polynomial. So the Galois group of splitting fields of polynomials of small degree. Of small degree. And by small, I mean actually just 2 and 3. That's what we're going to discuss. Okay, so first thing, well, the quadratic polynomial. So quadratic polynomials. Okay, so let's take a polynomial f in f bracket x, degree 2. And let k be a splitting field of f over f. Okay, if our polynomial already splits over f, Well, then the splitting field K is just F itself, and then the Galois group of K over F is just trivial. Right? You'll be interested in automorphisms of F that fix F. Well, that's just a trivial automorphism. So if F splits over F, the Galois group is trivial. Of the splitting field over F is trivial. So let's assume that, so we're going to assume that F does not split over F. But because the degree is 2, that's the same as saying that F doesn't have any roots in F. Or equivalently, that F has no roots in F. Right? Because the point is that if it does have a root in F, then because it has degree 2, it would actually have to split. Right? Because if it has a root in F, it will have one degree 1 factor with coefficients in F, and then by the division algorithm, you get another degree 1 factor as well, the polynomial splits over. So we're assuming that F doesn't have any roots in F. On the other hand, having no roots in F, well, because the polynomial has degree 2, is the same as being irreducible over F. So, or that F is irreducible over F. Okay, so we've got this polynomial of degree 2 over F, and we're assuming it's irreducible over F, and K is a splitting field of it. Okay, so the Galois group of K over F, well, you can actually think of that as a subgroup of the symmetric group on the set of roots of F. So these being roots of F in K. Okay. How many roots does F have in K? F is an irreducible polynomial of degree 2 with coefficients in F. How many roots does it have in a splitting field? You want to say 2, right? You tended to say 2, but you have to be careful. So there's a question of whether it has repeated roots or not. Right? If it doesn't have any repeated roots, then you're absolutely right. The degree is 2, so in a splitting field, it will have 2 roots. Absolutely. So now let's assume that the characteristic is not 2. Suppose that the characteristic of F is not 2. Then, see, if the characteristic of F is not 2, think about the derivative of the polynomial. Right? If it's a polynomial of degree 2, when you differentiate it, okay, so what does it start with? So if it started before with like ax squared plus dot dot dot, now it's the derivative, so this being f prime starts with 2ax plus something, right? Now if, well, and a is not 0 because we said f has degree 2. Now, if the characteristic is not 2, well, 2a won't be 0. It's a product of two non-zero things, so it's not 0. So f prime has degree 1. F prime is not 0. So you've got an irreducible polynomial f whose derivative is not identically 0. It's a polynomial, it's a non-zero polynomial. What does that tell us about the polynomial f? It tells us that f is separable. It has no repeated roots, right? Remember in your assignment you had And yeah, so on your assignment you had this question that if a polynomial, if an irreducible polynomial f has repeated roots, then the derivative of f must be identically zero, must be the zero polynomial. Well, here the derivative of your polynomial is not the zero polynomial, and your polynomial being irreducible. That means that this polynomial doesn't have any repeated roots. If the characteristic is not 2, then f is separable. Right? Because it is irreducible, and f prime is not the zero polynomial.